So we take the ball and throw it up at 20 meters per second. And we want to know when it's at its apex, so when it stops moving. So basically, we know that, let's see, I guess the best equation to use would be the V2 is the V1 plus acceleration times delta t. And this is set up so that we want this second velocity in this form, but we really don't. What we're after right now is delta t. So we're going to switch this up. We're going to say delta v, which is just the change in velocity, and that is equal to a delta t. So really all we did is move the v1 over the other side there. And then delta t, we have, so delta v over a is delta t, and that's just dividing both sides by a. So now, if the change in velocity has to be 20 meters per second, right? We have to be careful about positives and negatives here. So the change in velocity is going to be pointing downward, but the acceleration is going to be pointing downward too. So we can have those negatives cancel each other, or we can just pretend that they never were negative in the first place. We can just kind of redefine down as being positive. So now the change in velocity, in order for it to go from 20 meters per second down to 0, has to be 20 meters per second. And then the acceleration is the acceleration of gravity, so that's 9.8 meters per second squared. So we're going to do some canceling here. That meters cancels with that meters. That second cancels with the second squared. And this second transitions up to the top because it's in the denominator of the denominator. So that's the same as the numerator. So now, essentially, we're going to kind of cheat a little bit here and pretend that this 9.8 is 10. And then we have 20 divided by 10, and that's 2. So we're going to say this is roughly equals to 2. And that's the units on that is seconds.